Welcome to the EROS User Experience webinar series, where we talk to staff at EROS to learn more about the data, tools, and services coming out of the USGS Earth Resources Observation and Science, or EROS Center. Today's webinar is entitled An Introduction to Landsat Data Access and Processing in the Cloud. I'm your host, Danielle Golan, the Remote Sensing User Services Lead here at EROS in Sioux Falls, South Dakota. The time is currently 12 p.m. Central, so we'll go ahead and get started. First, a few logistics. To ensure the best audio experience, all participants have been muted. If you have any questions or comments during the webinar, please add them in the chat and we will address them at the end of the webinar. If the chat does not work for you, please feel free to email your questions to custserve@usgs.gov and we will answer them there. Today's webinar is being recorded. The recording will be available later on the USGS Landsat website, as well as the USGS Training's YouTube channel and the USGS Media Gallery. At the start and end of the webinar, we will have a few polling questions. These polls are optional, but your answers can help us create a better user experience in the future. The polling questions will be available via the polls feature in Teams or in the Teams chat for our audience members who are not able to use the Teams polls feature due to their organization settings. If the polls features do not work for you, please feel free to respond to the polling questions in the chat instead. The questions are the same, so please either use the polls feature or the chat, whichever option works best for you. And I will go ahead and launch our polls now while we finish the introduction to the webinar. You should now be able to see the first set of polling questions, both in that polls feature or in the chat, so feel free to fill those out at your leisure. Today's webinar will consist of a presentation, several live demonstrations, and then a question and answer session at the end. Today's speaker is Tony Ann Robinson, a geospatial cloud support scientist with the USGS EROS User Services team and the annual National Land Cover Database, or NLCD, team here at the USGS EROS. A graduate of the University of South Florida in Tampa, Florida, Tony Ann has a PhD in geology, focusing on geophysics. Tony Ann has worked as a contractor at EROS since the summer of 2023. Tony Ann's presentation will provide an overview on Landsat data in the cloud, as well as demonstrations of several scripts Tony Ann and the team have written on accessing and working with Landsat data in the cloud. Once Tony Ann has finished her presentation, we will then transition over to an optional set of final polling questions, and then we will move on to that Q&A portion of the webinar. We have several EROS staff members from User Services, the internal Landsat science team, and our Access and Archive cloud developers here at EROS on the line to help answer any questions you may have after Tony Ann has finished her presentation. Again, please feel free to add your questions or feedback throughout the webinar using the webinar chat. We'll try to answer all of our questions within the time allotted, but if we're not able to address your question during the Q&A portion, we will follow up with you offline. If there's a future webinar topic you would like us to cover, please feel free to suggest that in the chat as well. With that, it's my pleasure to introduce today's speaker, Tony Ann Robinson. Take it away, Tony Ann.
Hello, everyone. I am Tony Robinson, and welcome to this introduction to the materials that we've created in the past year to help you guys get started with working with Landsat data in the cloud. To start, a brief outline. First, I'm going to discuss how Landsat data is stored in the cloud. I'm going to fully demo one tutorial and walk through the HTML format of two other tutorials. And then I'm going to highlight some valuable resources to help you guys get started with working in the cloud. To start, yes, Landsat data is available in the cloud. It's available in the Amazon Web Services S3 bucket located in the Oregon US West 2 region. Users will need to specify direct requester pays when they're accessing this data. So what is available in the cloud? So currently we have level 1 Radiance products, and these are the geometric and radiometric corrected products. Level 2, which are currently the atmospheric corrected products, and they're the surface reflectance and the surface temperature products. And then we have the ARD analysis, which are analysis ready products that are available. For level 3, the burnt area, the fractional snow area, and the dynamic surface water products are available. So how is data stored in the cloud? So here's an example with a level 2 product that was collected with the thematic mapper in 2011. And this is the product's full name. Where is it stored? First, it's stored in the S3 bucket, the USGS Landsat S3 bucket. And this is a surface reflectance data product, by the way. It's stored first in the USGS S3 bucket. It's stored under its collection number, which is 2, and that's highlighted in the name. It's then stored in its level number, which is level 2, since it's a level 2 product. It's then stored under the projection, which is a standard projection, and that's not highlighted in the name. And the standard projection in this case is the WGS 84 UTM projection that is used. It's then stored under its sensor. In this case, it's a thematic sensor, which is labeled as TM here, but labeled as T in its name. It's then stored under its year, which is the year it's collected, and that is highlighted in its name. And then it's stored under its path and row, which are also highlighted in its name. And lastly, it will be under its entire product name. So under this product structure, there are various objects ranging from the metadata to banned products that are downloadable for this specific product. Now that you know how the data is stored, now let's walk through how to find this data. And the first step into finding the data is understanding how the metadata is structured. So Landsat uses the STAC, which is the Spatial Temporal Asset Catalog, and it's just a family of specifications that standardizes geospatial metadata. So it makes it easier for you to access the metadata related to geospatial products. So we have a Landsat STAC catalog, and the Landsat STAC catalog includes various collections, and these collections are groups of Landsat products. For example, a Landsat STAC collection is the surface reflectance collection, for example, which is separate from the surface temperature collection. There are about 14 Landsat STAC collections. And within each collection, there are individual Landsat data products, and those are referred to as STAC items. And lastly, within each item, there are various assets, and these range from the thumbnail, the metadata, and the various links to download the data that is available per the item. We have various ways for you guys to interact with the STAC. The first one here is the Landsat STAC browser, which is available through the USGS. It's really a way to just click through based on the scene, the tile, or a level 3 product, just to find a product to see what is available with this product, what metadata is associated with this product. And this is the non-programmatic way of interacting with the STAC. And here's an example with a burnt area product. This single product, upon clicking through to find this product in the Landsat STAC browser, you will see the outline of this product. You'll also see the metadata to the right, and there are tabs on top that can click through to see the assets and the various bands and the thumbnail. The second way to non-programmatically interact with the STAC is through the STAC index. STAC index orders all of the Landsat STAC collections first. It starts with the collection names listed with their title. There are 14 of them. You can click through any, depending on the product you want, you can click through to find individual scenes and see where they're located on the map, and you can see the various data associated with them. Similarly, this is an example using analysis ready dataset. Here is the outline of the scene, and also the metadata is located on the right. You can scroll through to see what is associated with this data. So programmatically now, in the USGS, specifically the user services, we provide scripts, Python notebooks to show you how to work in the cloud with Landsat data. And they're housed in the USGS GitLab that is just highlighted here. I'll be going to the GitLab after this brief introduction to it. What is available in the GitLab? We have 4 projects related to the cloud. First one is about accessing data, which is how to search and pull down data. The second is processing, which is anything from calculating indices to filtering and also visualizing. There's a lot of visualizing, of course. There are quick guides, which are short guides of how to do something like create a GeoJSON file. And there are case studies, which are newer, and they're real-world examples of how to process Landsat in the cloud. From here, I'll be going to the demo. First, I'll briefly mention the 3 tutorials that I'll be walking through. The first tutorial is just an introduction to STAC. This one, I'll actually be downloading it and running it live. The second one, this is just related to decoding the pixel mask and using it for masking. I will not be downloading this, but I'll be walking through its HTML file. And the third one is related to pulling down a single pixel through time and filtering it and also calculating indices. So with that, I'm just gonna head over to the GitLab and introduce you guys to the GitLab. So here is the USGS GitLab. I am not signed in so that you can see what is readily available to you as a user. As you can see, there are 5 projects. I discussed the ones that are related to cloud. However, we have a machine-to-machine project available, which it just focuses on pulling down data using the machine-to-machine API. Since it's not cloud, I did not discuss this, but we have 3 machine-to-machine projects that are tutorials that are available. In every cloud tutorial, we currently have about 6 tutorials in accessing, all related to interacting with the Stack API to pull data down. In case studies, we currently have 1, which is related to compositing in the Ucayali region in Peru. In processing in the cloud, there are about 7 and more pending to be uploaded, various ways to process and filter the data. And in Quick Guides, currently have 2 guides related to creating GeoJSONs, which are really great source in searching or interacting with the stack to find, using GeoJSONs to search and find data. So before I actually download the first tutorial, which I'm going to fully demo, I'm just going to go through and show you, for example, how the tutorials are set up in the GitLab. So here's an example with the recent creating composites in Landsat data tutorial. In every tutorial, there is the notebook, the HTML file of the notebook that is ran. There is an access YML file, and that is just the file that you use to create your Python environment. Sometimes there are data files with just images outputted and util folders, which include the GeoJSON that is used for the area. The README file is presented below the list of the files, and it's really just the introduction to the tutorial itself, which introduces the tutorial of compositing, where it's located. And for every processing, there are prerequisites that is listed and a tables of contents so you can see what's in the tutorial. And lastly, and importantly, we also have how to set up the Python environment using the YML file that is given to you as a user. This is what is provided with the tutorial. So I'm going to head back out to the main branch, and I'm going to go find that tutorial that I will be demonstrating, and it's the introduction to the Landsat stack, which is a great starting point if you're interested. So I'm going to first copy the HTTPS link for this to pull it down using Git. So I'm in an empty directory that I created for this webinar, and I'm just going to activate that environment. It's already created, but I'm just going to activate it to get started, the accessing Landsat data. And then I'm going to say git clone, and I'm pasting that file for the tutorial, the link to the tutorial, and I'm pulling it down into this directory that I have open for this webinar. To open the tutorial, I'm going to open Jupyter Notebook. All the tutorials are Jupyter Notebooks, which we refer to as Python notebooks. I'm going to open the tutorial, and there is everything associated with this one. This one comes with a HTML file that shows before running it and one for after. And of course, the YAML file, if it's necessary in this case. So I'm going to open the notebook, and we're going to just start running through this tutorial. So again, this is a basic introduction to Stack, the Landsat Stack specifically. Stack is a standard for grouping geospatial metadata, and we use Stack here at USGS for Landsat, especially if you're trying to get Landsat data from the cloud. So that is the introduction to Stack. And yes, the topics covered what is Stack, importing packages, and then interacting with the API, and also showing you how to search for data. Again, we have Landsat has a Stack API, which is just a link that you interact with when you're programming. The Landsat Stack catalog, and I wanted to emphasize this, that I do use the term collections. Landsat Stack collections are groupings of Landsat data, while Landsat Collection 2, it's really a processing of the entire Landsat archive, and we are currently at Landsat Collection 2 in terms of archival processing. But Landsat stack collection, when I refer to collections moving forward, I'm referring to just groupings of different Landsat data sets. So we have the Landsat stack catalog, and within the catalog, there are collections or groupings of data sets. And within each collection, there is a stack item, which is the scene itself, multiple Landsat scenes. To start, we're going to only import a single tool here, which is just request. To interact with the Stack API, you do not need Amazon Web Services account set up. It's really just making sure you have the whatever program you're using or module you're using to pull the data. Here, I'm just pulling down using the request function to interact with this Landsat Stack server and pulling down the response. This is the various links and the versions and the title of the API that are pulled down. So really just GeoJSON, just the various links that are attached to the Landsat stack. And here again, we're printing some of the more useful links. Some of these, if you click them, you will find the various ways that you can search in the Landsat stack. However, the tutorials kind of highlight more clearly how you can search, but they're available within all the links that are available in the Landsat stack catalog. Here, I'm just printing the information, the useful information related to it, the version, the ID, and the type. It's a catalog, and there are 22 links associated with it. Next, I'm running this cell, and it's printing all the children and various information related to the links. The Landsat 14 collections that are available, the stack collections, are listed as children in the catalog, child items. So for the multiple stack collections, there are 14. So this cell, let's count how many collections are available, and there are 14 Landsat groupings of products. And again, that is the burn area versus the surface reflectance versus level 1. They're all grouped separately. And here we're just listing all the collections and the descriptions for all the collections, all 14 of them. And here we're actually looking at one of the collections, the second collection, because Python nomenclature is really, one is actually a second. So the second collection is the surface temperature, and within the metadata for this entire collection, you have the bounding box, the license. The keywords are actually the platforms that are used to collect data for this collection, and there are various links, just the endpoints specifically to this collection that are available. So within each stack collection, there are multiple items, and these are called stack items. And these are single data products. So a single scene collected in a specific time, wherever it's been collected. And here's a single product, and it comes with a lot of metadata. It comes with its ID, of course, its bounding box, its geometry, properties, and if I scroll further, there are assets. These are broken down further in the tutorial, so I'll just move on to those because it explains. So within this single scene, which is a surface temperature scene, since we had that collection selected, you have the description of it, its ID, its acquisition date, the platform that is used to collect it, cloud cover, and a number of assets, so which are the bands, the metadata, and even the thumbnails. And here in this cell, I'll be just printing out the various assets that are associated with this single scene and URLs. So there are multiple URLs attached to the products. So you can have the Landsat Look URL. You can individually click the Landsat URLs to download products if you'd like it that way. But however, Stack is best used if you're interacting with the cloud or pulling data to the cloud, because every asset has a S3 link where you can use Amazon or REST Stereo or a Python library to pull it down. But they do all have links that you can click if you're interested in doing that. And I won't click them, but they're there and they work. Next up in section 3, we're just setting up a search. And this is really just creating a parameter dictionary to interact with the Landsat stack endpoint. So first step, here they're just pulling the link from the Landsat stack endpoint link from the catalog that was pulled down, and also creating a empty parameter dictionary to start. So that just creates an empty parameter dictionary. Here in this section, it's really just parameters that we're going to search and are available for you to search, but there are more that are available to search. And I will show you those when we move deeper into the tutorial. The limit, we're first setting a limit, and you can set a limit of up to 10,000, but here is 400. So every item comes with a bounding box. And here's an example. If you know the bounding, or if you want to use the bounding box of an item, you could use it by just specifying it. But here we're setting a bounding box in a different area for our search, just to not pull in the same item that we were using or looking at. So we added a bounding box here to the parameter dictionary along with the limit. And now we're doing a search. And what is expected from this search is 400 to be returned, because there's a limit of 400, and we expect more than 400 data sets to interact when you're only just specifying a bounding box. The next step is adding a temporal query, and this is really just what they call an isostring datetime object you include into parameter dictionary. I'm going to run that to add it and see it's updated with the datetime to the dictionary, and then I'm going to run it. So now we're limiting the search to a specific date range, and now it's 144 products that are returned. And reminder, we can specify collections, and I'm going to be going ahead into that. So in section 3, you can specify a collection, and in this case, you are specifying the two collections, the surface reflectance and the surface temperature, to further limit or restrict this search. So we're adding two collections to it, to the parameter dictionary. And here in 20, I'm going to run with the collections added, and now we've reduced from 144 to 28, since only a few of the products were actually from the surface reflectance and surface temperature collections. Next, again, we're printing the single item, and the first item that is returned is a surface temperature product. And again, it has all metadata associated with the product, the geometry, the ID, the properties, and the assets. So in this section, line of code, I'm going to run this to show you guys the various properties associated with the single item. And this is important because these properties are what are searchable for this item. So everything from the date time, the cloud cover, the scene ID, even the projection shape are searchable using Stack for this item. And you search properties by creating a query or adding a query to the parameter dictionary. And in this section that I just ran, we're adding a cloud cover range from 0 to 60% and restricting it to platforms only from Landsat 8 and 9. And I'm going to run to see the results, and the results show only 12 returned for that specific date range, bounding box, collection, and cloud range and platforms. So here in this very last cell, I'm just going to run to show you the results. So after all those specifications, we only have data from Landsat 8, Landsat 9. They only have cloud cover below 60%, and they're all from the surface temperature and the surface reflectance data sets. Thank you to Holly for creating this introduction to Stack. The next two tutorials I'm going to walk through are the HTML formats of them, and they're related to processing Landsat data in the cloud. So to start, I'll be heading to the decoding the pixel, Landsat QA pixel, and using it for masking tutorial. So the Pixel QA band, it's really a quality layer that highlights the potential issues with the pixels that you're working with for any Landsat scene. It's a 16 unsigned bit cloud optimized GeoTIFF, and it's downloadable through the S3 bucket as is an asset with all the products. The Pixel QA, you can mask out clouds, snow, shadow, water, and other potential issues with your pixel. So in this use case example, there's not much of a story. It's really just, here's Vancouver. I know it has snow and ice. I selected this scene because the main focus is how to process the Pixel QA band and use it with Python. This is the before and after result, which will also be shown in the end. So to start, we have the various prerequisites that you can use. If you don't understand something, the information will be found in the prerequisite tutorial. We then import the modules, more Python modules in this case, because we're actually pulling data into memory. So the great thing about working with data in the cloud is that you're pulling data into memory. You are not downloading them directly to your device, your computer. So the first step in many of the tutorials is creating the functions to interact with the Landsat Stack server. And this one is just a fetch stack server that I've been using. There are other tutorials that use the famous PyStack. The earlier tutorials like this one, they use this fetch stack server that we've created. And it really just uses the requests and catches errors if they're present. The next step is creating a parameter payload function, which is really similar to what I did previously, where we created the parameters that for searching. However, this is a very elaborate one. In a sense, since it's one of the first tutorials, it's supposed to show you the various ways to set up the parameter dictionary and the things that you can include in your parameter dictionary if you would like. That's how specific you want to go with your search. The next step is reading in a GeoJSON file. All the tutorials pretty much, most of them use GeoJSON files. Some of them I create the bounding box in the tutorial, but this one I'm pulling a GeoJSON file into the notebook for use. And this GeoJSON file is in the WGS 84 reference system. The next step is plotting. We often create maps. Of course, we're working with imagery from the Earth, and here is an outline of the area plotted using the GeoJSON file that is imported. And we use Folium for this plotting. So in section 3, I'm just setting up to interact with the Stack server to get the metadata associated with the scene that I want to pull down. So I'm really just setting up a BB box from the GeoJSON import, the area of interest. And I'm here only really using a single query. And remember, a query is the various properties in a scene that are searchable. In this case, I'm using the scene ID property to search for this scene, because I know it's just going to bring me back what I want, the single scene that I'm interested in. And here it's just, I'm putting everything on a single line to create the parameter dictionary, and in this case, I'm searching for the surface reflectance data. Now, in this section, we're just entering the parameter dictionary and then retrieving the product that is returned. It's one item. I know it will be one item because it's only one scene that is in the surface reflectance with that scene ID. And here I'm just extracting the only item that is returned. In this step, I am listing the band names. So Landsat band names are present within the assets for a single product. And here I'm pulling the shortwave infrared, the NRI, and the red band names. With the band names, I'm then parsing the query, the single items assets to find their S3 links for download. And then I'm saving it into this band links variable. Here in this section, I'm showing you what assets are available in terms of bands or with data for this product, and it ranges from the coastal to the SWRI 22, the SWIR 22 band. Next step is very important. In every tutorial, especially related to processing, I discuss AWS and what is necessary. You need to have an AWS account. You need to specify direct requester pays when you are accessing Landsat data in the cloud. And here are two ways you can set up your AWS credentials for interacting with or pulling down Landsat data. And here it's a simple function that uses a rasterio for pulling down the data and cropping it to that bounding box that was imported as a GeoJSON. So the next step is pulling in the bands into a single spectral array. And here I'm using that function, the retrieve cog XR, to pull them in a single spectral array, which will be a 3-banded array with its X and Y length here printed out. Next step is plotting to visualize the results. And here is the before of the image as a composite of all 3 bands. The next step, of course, since it's about pixel QA, we're pulling in the QA pixel. First, pulling it in as a GeoJSON product, then I am pulling in the link and using the XR function to pull it in as an X-array product, which is just an array of the data set, and it brings in its coordinates and other spatial metadata associated with it. So it's a single banded array. In this section, I'm just listing the various flags that are within the QA pixel depending on the satellite. We can assure you that what's available in Landsat 8 right now is also available in Landsat 9, and only bits 14 to 15 aren't available for Landsat 4 and 7. And in this section, I'm just printing out the descriptions and the bit locations for the bits that are available for this QA pixel band. Next step is masking. We heard this section is very elaborate, very long. It shows you step by step how to decode the QA bit and explain bit coding so you can understand what is going on in the functions that are presented. So this entire section here is how to decode the QA bit, what do the symbols in Python mean when you're decoding the bit, and how to do that for a single bit. So upon reading this, you may actually understand how to decode the bit. And these functions, these 2 functions, decoding the bit and the masking, they work together to decode a bit and to mask it per whatever obstruction you want to mask out, whether it's clouds or shadows or water. So the QA mask, it uses this decode bit function to decode whatever bit is located in a pixel location for the QA mask. And it includes all of the maskable obstructions that could be caught in your pixel, and also includes the confidence mask and how you could do it. It's very long. Again, it's just, we're not using all of these. There's just so you to understand how to use it to mask. In 4.2 here, I'm applying the masking, and I'm only masking for clouds, snow, and shadow, and I'm creating a QA mask. Here in this next bullet, broadcasting that mask to the same shape as a QA, the spectral array, which includes 3 bands. So now the QA mask is now 3-banded, of course, the same X and Y range as the spectral array, just for a quick masking. In this section here, I am masking out the spectral band, which includes all the bands that were pulled in the 3 bands, and using the QA mask, and fill in areas that are snow, clouds, and shadows with 0. And the next step is plotting, just a single plot for after the masking is complete. You can see that majority, not all of the cloud and shadow and snow pixels have been masked out using the QA band. And in the end of every processing tutorial, there's some evaluation, some discussion, some comparison. So in 4.3 here, I'm just, again, plotting the same results, however, side by side, for you to see the before and after of the results of decoding the QA bit and masking for Vancouver, Toulouse snow, clouds, and shadows. So with this one done, I'm going to move on to the last demo, which is the retrieving a single pixel through time. And it's really focused on how to just use one point to get data within whatever date range you'd want for Landsat and whatever type of Landsat data you are pulling down, what grouping. So for a single pixel, this tutorial is really a time series tutorial, but of course it introduces point feature analysis, time series analysis, and it could be your starter for a change detection analysis. The use case scenario for this tutorial is a sinkhole that happened in July 2017 in Florida. It is called the Lando Lake sinkhole. It swallowed 2 houses and many were condemned surrounding it because that's how large it was. So what we're doing with this single pixel is I've selected a single pixel inside this sinkhole, and I want to see how does this pixel through time, how does it appear through time before and after the sinkhole collapse, and can we see the sinkhole collapse in the normalized different vegetation index, the NDVI index, which is the vegetation index where high NDVI will indicate presence of healthier vegetation, while a lower one is unhealthy or just presence of water or no vegetation. So can we see this collapse in the NDVI value in the sinkhole through time? So this image here is the Google image of the sinkhole, January before it collapsed, and then the May 2023, 5 years after its collapse. So it's been through stages. You can even see mowing in this one, like a bit. So to start, prerequisite tutorials. If you are stuck somewhere, you could find the information in prerequisite tutorials. Table of contents, what is available in this tutorial. Next step, importing all the modules that are used from Python for this. A lot of rasterio. Next step in section 1, of course, setting up the fetch function, interacting with the Landsat stack server. And next, of course, setting up the query function. This one, it incorporates the fetch function in the end with the parameter. It creates a parameter, then it just pulls in whatever metadata. And it's hard-coded for surface reflectance because I'm really only pulling it in for this tutorial. And it's much shorter because it's like, let's just get to the point. For this one, this is one of the tutorials here in section 2 that I create the object in the tutorial itself. So here I'm just creating a JSON point that I'll be using throughout the tutorial. Well, not throughout, just to pull the data. So these cells are really just, here's the GeoJSON, I'm printing it. I like printing things so people can see what it's supposed to look like, just in case something goes wrong. So that's what's happening here. Here I'm setting up the folium map with that single point. I will not be displaying it as yet. So before I display this one, I'm going to pull in the data. So some of them I pull in the data, the metadata, so I can actually print the outlines on folium. So here in 4.8, I am setting up the stack, querying and pulling in data that intercept that single point for the date range, January 1st, 2016 to January 1st, 2024. All surface reflectance that was hard-coded in the querying. And next, I am now using folium. I've added those returns to the map, and here they are plotted. Good news about folium is that you can actually work with it and zoom and interact with it. It's just an HTML file, like the one I'm on right now. So here is the sinkhole. It's on Ocean Pines Drive. It is in Land O'Lakes, Florida. This is how it looks on this map. And there's that point that I'm pulling in, point of data. And these blue lines are the scenes that intercepted. So this tutorial is focused on calculating the NDVI, but to calculate the NDVI, which is the vegetation index, you need really only the NRI and the red band. But before I get to that, this section 3 here, I'm just pulling in all spectral bands, the blue, green, red, NRI, SWRI 1 and 2. I'm just showing you, here's how you would pull in all spectral bands. So how to do this by interacting with the returns from the stack is you list the band names. You can list the band names based on what order you actually would like them to pull in. And I'm just leaving them in whatever order that I tend to think they're in this order. And here I'm just showing you how to interact with a single item to pull in all the band links, the S3 links for them into a variable list. Again, these are the assets that are available, the different bands that are available for download. I'm not pulling down the coastal band, but I'm pulling down the blue to the SWRI. Again, every tutorial includes the AWS warning. Sometimes it's blue. This is how you set up. You need to specify direct requester plays. Next step is the function for actually pulling the data using the rasterio. And this one is just for pulling a single point and returns the values. Here I'm doing some sequencing here in 4.15 using the band links, the links of the S3 bands, and pulling in each one by one and putting it into a single array. And it's in the order of which you name the bands. So that session, I really just had to pause and say, I have not shown you how to pull down the list of bands. So before I jump into the tutorial, let's show you how you would list them. and then I jump into the tutorial and pull in the data. So now in section 4, I'm jumping in and I'm only pulling in the NRI, the red, for all of the items that are returned for that single point between January 2016 to 2024 January. And there are 516 data products, and I'm just clipping a single pixel from each of them using the point object. And this is just the printout of what is happening in the background. So here, now that we've pulled in all the data, the NRI and the red bands, here is just a view of the array itself, which is unsigned 16-bit. And this is what we will call a pixel rod because it involves band values through time. So if you see the term pixel rod or spectral rod, it could be spectral values through time or pixel values through time for multiple bands through time. So here, the left column would be the NRI and the right would be the red, because that's how I specified pulling them in. Next step is retrieving the acquisition dates, and that can be pulled from the query items. So I'm pulling in point dates. In section 5, we are pulling in the quality assessment. I'm just doing a simple quality assessment here. Nothing that stressful. Could do more, but I'm pulling in all the quality assessment links and then all of their values from all 516 data sets. Here in 21 to 24, it's really just cleaning up the data. Let's find all the nans in the van values and remove them from the point dates, the QA values, and the van values themselves. Next step is now let's do some masking. Here's a shorter QA masking function that includes its decoding in its return. So create the QA masking function. Next step, let's apply it. Here in section 26, I'm applying it to only remove clouds. I'm not that stressed about anything else in Florida outside of clouds. The next step, we're using that quality assessment array to remove the point dates and band values that are for the products that have clouds, or those point locations that have pixels that have clouds. And the final stretch is calculating the NDVI. So before calculating the NDVI, we scale the data using the scaling factor for Landsat collection 2 and the offset. So here we're just scaling in 29, and next is calculating the NDVI, which is really just a ratio between the NRI and the red bands. And here's the NDVI variable here in 30. Last step, converting the dates of each remaining pixel to decimal years. And you're going to see so many helper functions within the tutorials, and this is a helper function that's just, here's how we're converting to decimal year. And lastly, we are putting everything together. We are plotting the NDVI through time in this cell, and here it is as a plot. So the plot shows the single pixel location through times after calculating the NDVI, which is on the y-axis, and the time is on the x-axis. The sinkhole collapse is highlighted in red, and the NDVI values are in blues. So we see that prior to the sinkhole, the NDVI values were, of course, seem a bit cyclic, but after the sinkhole, there is a drop in the NDVI. It could be an indication of the introduction to water or the change of the brightness of that soil that they used to dump it up. And then you see that NDVI increase years after to its cyclic pattern of values. And so this is a great introduction to using indices and index, and also working with a single pixel through time when you're processing Landsat data in the cloud. And again, you're not downloading the data, you are pulling in only values for that single pixel. So with that, I'm just going to return and finish up the presentation. So we just went through the retrieving a single band tutorial, and now I'm just going to close off with just some available cloud resources. So what cloud resources are available? Let's start with Pangeo. These are available at no cost. Pangeo provides cloud computing resources for geosciences. You can access it through the Pangeo link that is provided here. Then we have the NASA Earth Data Primer that has a lot of information related to AWS cloud services. You can learn how to set up, understand pricing, costs, etc. It's a great resource. Third one is the Alaska Satellite Facility Open Science Lab. I personally started the cloud years ago when they had Open Star Lab. You would have to sign up and you get a Jupyter Hub where you can even pull down the tutorials to work in the cloud. It's a really great source for people who want access to a Jupyter Hub that they can work in the cloud. Then next you have OpenScapes, and this is a combination of a community, and you also have a Jupyter Hub. It's called a 2i2c Jupyter Hub Access. You would need to sign up to be a part of their science cohort. Go to the link provided. And again, a great resource because it has a community of geoscientists who are willing to help you get started in the cloud. And lastly, cloud native, just like NASA opens, all of these are communities really. It's a community. You can collaborate, you can work with various data scientists and connect to understand how to work in the cloud and get started with working in the cloud. They even have conference. And with that, thank you for joining us today. You can contact us at the following CustServe email, and also please go to the GitLab.
Great. Thank you for a great presentation and for showing us those really cool demos, Tony Ann. For those listening in, I've added some final links to the chat, which include more information about Landsat commercial cloud data access, as well as how to sign up to be notified about future webinars, and a link to watch some of our previously recorded webinars, where this webinar will be uploaded to in a few weeks. At this time, we'll now move on to those final optional polling questions portion of the webinar. So I'll get that launched, and I'll get those loaded in chat. You should now see the polling questions on your screen or in the chat. Please take a few minutes to respond to those questions. Reminder, these are the same set of questions, so please only answer once via either the polls feature or via the chat, whichever option works best for you. If you have any final questions or feedback about accessing or working with Landsat data in the cloud, perhaps any scripting ideas you'd like to see added to the code.usgs resource, feel free to add those to the chat now as well. With that, we'll give you a few moments to answer those polling questions and submit any final questions or feedback you have in the chat. And since we're at 12:55, we'll go ahead and start answering some of the questions that we have. So feel free to keep answering those polling questions, but now we'll go ahead and start to field questions from the audience. The first question that we have is, thank you for the great presentation. I'm doing research on dust storms and needed to download land cover data for 460 locations in the US for different years. The user has coordinates for the 460 locations and they need to download MODIS land cover data. They're wondering if there's a way to automate the process instead of manually selecting and downloading the land cover instances. So for that user, if you haven't yet, there's several options. I recommend accessing MODIS land cover data via the Appears point sample. I think that'll work excellently for your resource as you can upload those coordinates, or the Appears API, or via Earth Access. And actually this summer, we're planning on giving a webinar about how to use Appears. So make sure to stay tuned to that. I see Cole has posted the link in the chat. So thank you very much, Cole. And I'll also post a link to Earth Access in case that's something you're interested in learning more about as well. Our next question, is the new data available first via S3 or machine to machine? And I can also answer this one. So technically the data is available first through S3 over the machine to machine, as the machine to machine API has to wait for updates on cloud locations. It may also be slow depending on how many users are requesting data via the machine to machine at that specific time. But the difference really is relatively negligible. It should be within the same hour. So you could access them either way. Really, there's not much of a difference between when you'll see it in S3 versus machine to machine. The next question we have is, will the slides be shared? Yes, we will be posting them on the Landsat website when the recording is posted, and we'll make sure to advertise that out through the different channels where we advertise the webinar. So make sure to follow up there. The next question we have is it easy to simplify the code?
Can they expand on that?
Yeah, feel free to add to the chat if you have any explanation for your question. The code is pretty simplified already, and one of the great things about these scripts is they're just really examples. So we encourage you to adapt them, fit them to meet your own needs, simplify them as much as you would like. But if you do have a detail for your question, let us know. The next question is, do you need a password to access the page?
No, you don't need a password to access the page. The GitLab page that I actually clicked through and demoed, I actually wasn't signed in, and so anyone Even without a GitLab account, you can access that link.
Perfect. Thanks, Tony. Let's see. Someone asked if the webinar is being recorded and where the YouTube channel is. I did post that as part of the final links. So there is the USGS Training's YouTube channel. You should see the link for it in the chat. Let's see. Are these data time scaled? What is the extent of the spatial extent?
It depends on the data set you're actually trying to retrieve. For example, the fractional snow cover for the US, it's only available mainly in the north and the west of the US. The extent depends on where your study area is and what you're trying to process or what information you're trying to get.
Definitely. And Jacob, would you like to expand a little more on Landsat?
Yeah, so specifically on Landsat, it's recorded on a 16-day revisit period, meaning that, if you're looking at Washington, D.C., you get a picture today, you can expect a new picture about 16 days from now. And with Landsat 8 and 9 both currently operating, they operate opposite each other. So that 16 days is actually cut down to about 8 days. And so new Landsat imagery is actually being acquired every day, but that doesn't necessarily mean that it's going to be over your area of interest.
Perfect. Thank you, Jacob. And we are at the hour, but we'll try and answer the last couple of questions we have real quick. But feel free to hop off if you need to. We totally understand, but we'll work on answering the rest of these questions. The next one is there a participant certificate awarded for attending these webinars? Currently, that's not something that we offer, but we do thank you for joining us. We also had a user that asked, do you really need a JSON file? Can't we export in a shape file, a text, or a CSV file?
You can definitely use a shapefile. You can just extract the bounds from the shapefile to create a bounding box and interact with, and then pull in data for that shapefile. One big problem with shapefiles too, and also large GeoJSON files, is that if your area is really huge, you'll get an error from the stack server. For example, if you search up the ukulele region in Peru, that's an area that would be too large. Or if you have a shapefile for an entire Florida, that would be too large to use in the stack server.
Excellent. And we did have some great discussion going on in the chat about JSON files. So thank you for everyone who recommended resources there. Someone asked if this video will be downloadable. It will be shared on that USGS website and on the USGS YouTube trainings channel. So you can access the video there. The next question we have is, in your second tutorial, you substituted bad quality pixels with the value of 0. Is it better or possible to substitute them with nons?
Oh yeah, you can definitely substitute them with nons using Xarray. I just did zeros that time. But I have a tutorial that's not published yet related to using the fractional snow layer for identifying snow. You can substitute nons. And when that's uploaded, you'll see the nons that are used, how they're substituted.
Perfect. Thank you, Tony. We also had a request for a course on GeoJSON, so that's something we'll consider. And then what about the temperatures as observed through multi-decadal Landsat stack datasets? And Madi, I'm not sure if you're asking that for a specific question before, if you want to clarify in the chat. All right. It looks like we answered all the questions that were asked. Madi, if you want to post in the chat real quick, we'll try and finalize an answer for your question. But with that, I did want to thank everyone for joining us. Don't forget, if you have any additional questions later about Landsat data in the cloud, any of the tutorials that Tony shared today, or any of the other tutorials that you can find on the EROS GitLab, or if you have any questions about any other data, tools, or services the USGS EROS provides, you can always email our team at custserve@usgs.gov. And I'd like to once again thank our speaker, Tony Ann, for her time and great presentation. And I'd like to thank you all for joining us today. We'll stick around a few more minutes to answer any other questions that come in, but we do hope to see everyone at a future webinar. If you'd like to be notified of when the next webinar will occur, please sign up for that EROS user group by emailing custserve@usgs.gov. And again, thank you all for taking the time to join us today. We hope you have a wonderful rest of the day. I see. Samara, you're wanting a course about GeoJSON. We can definitely have that.
In the quick guides, we have 2 mini tutorials on GeoJSONs and creating them from points to combination of points and lines to polygons, wacky shapes. They're in the quick guides.
I'll add a link to the chat for both of those. And then Madi, I hope you're pronouncing your name correctly, but they had the question about what's the temperatures as observed through multi-decadal Landsat stack data sets in the context of deforestation related to climate conditions.
Can we get some clarification on that question? Can anyone pitch in on that? I don't think I'm sure what's being asked, is it?
Yeah, Madi, I might have you email into that CustServe email a little bit more detail about what you're trying to do, and then we can try and help you there. All right. Any other questions or final thoughts? Okay, perfect. We're going to call it. Thanks again, everyone, for joining us. We hope you have a wonderful rest of the day.